In this video, we're going to look at finding the derivative of a natural logarithmic function. Before we do that, let's just talk about this natural log function for just a moment. When we find the natural log of any value, that value, x, must always be positive. Let's talk about y for a moment, just as a refresher. If I rewrote this expression, I can write this as y equals the natural log of x. And I know that a natural log is equivalent to log base e of x. So if I rewrite this logarithm as an exponential function, I can write this as e to the y is equal to x. Now let's talk about why x must be positive all the time. So if I think about values that I can put in for y, there's no end to what I can put in for y. So I can put e to the 0 in for y. And my output is the input for the natural log. So the output of this exponential was the input for the natural log. So let's look at these outputs for the exponential. E to the 0 is 1. E to the first is e. If I did e to the negative 1 power, that's not going to give me a negative number. That's going to make this 1 over e. So it doesn't matter what I put in for the value of y. I'll get some positive output every single time. There's nothing I can put e to the power of that will make e negative. So what that means then is if this output of this exponential must always be positive, then that means that the input of the natural log must always be positive as well. Okay, so that's why I put absolute values there, just so everybody is aware that that x value cannot be a negative number. All right, so down below then, I graphed the natural log of x. What I'd like you to do right now is, and we're not going to do this in a scientific way, when we find the derivative of this natural log, this is going to be an unscientific approach for now. We'll talk about it more later in a more mathematical way. But what I would like you to do right now is take a moment to graph the derivative of the natural log of x. So if you think about how we started this out, when you find the derivative of a function from its graph, you think about the slopes of all of its tangent lines. So I want you to take a moment, I want you to pause this video, and I want you to see if you can come up with a graph of the derivative of this natural log function. Make sure you're graphing the derivative on a new set of axes because the y-axis will be different on your derivative graph, even though the x-axis will stay the same. All right, so I'll pause. I'll give you a moment to do that. I want you to actually pause and go draw it and then come back. All right, welcome back. I hope that went okay. So I know that we're only dealing with the positive x-axis. So when I draw my new set of axes, and I'm going to draw it over here because I'm a little bit lazy, and I want it to just be on the same screen. I want it to be easy to see. So there's my positive x-axis with a little blip in it, and I'm going to draw, that's my y-axis, my bad, and here's my positive x-axis. Sorry about that. Okay, so here's my derivative graph. This will be the slopes of that function, and the x values will stay the same. So if I look at the original function, I see that the slopes are all positive. And I notice that when x is close to 0, the slopes are very, very steep, infinitely steep. And then as we progress and x gets larger, the slopes start to flatten out. So the slopes will approach 0. What that means is, since all of these slopes are positive then, I'm actually going to move my x-axis down. Okay. I'm going to move my x-axis down. I'll have to get rid of that line in just a second. There we go. I'm going to move my x-axis down because I only need the positive values on the y-axis. Okay, the slopes start out really, really steep. So I'm going to start out with a very steep slope up here. Notice I didn't put any values on the y-axis because we don't know exactly what those will be. And then as x gets larger, the slopes start to flatten out and become 0 or closer to 0. They don't become 0. they get closer and closer to 0. This kind of looks like a function you've seen before. The function, if I were to continue it on this other side, the function is the 1 over x, or the inverse function. Now we're only looking at the positive side of it, or the right side of this inverse function, because we're only looking at positive x values. Okay, so you just found the derivative of a natural log. That's all there was to it. So let's complete this sentence right here. So the derivative of a natural log is equivalent to 1 over x, looking at only the positive x values. Now when we write the derivative 1 over x, we don't need the absolute values because the absolute value was implied in the natural log. So we already know this is only the positive x axis, so the right side of the x-axis. Okay, let's practice this a little bit. If I give you a function like this one, and I ask you to find the derivative of it, we're going to do this like you would on any other. You're going to find the derivative of each part separately. So in this first one, g prime of x, the 6 is just a coefficient. So it's 6 times whatever the derivative of the natural log of x is. Well, that's something we just found. We know that the derivative of the natural log of x is 1 over x. And this next one just requires the power rule, so that's 28x. If we simplify that first expression, that's 6 over x minus 28x. You could go so far as finding the common denominator. The book would have done that. And if you were trying to find critical numbers or what have you, that could come in handy. But this is good enough. You found the derivative. You did what I asked. Okay, what if we have a different function? So for the second one, what if it's the natural log of 14x? How is that going to change things? I want you to pause again right now, and I want you to take the opportunity to try that. So we've got something different that we're differentiating. It's the natural log of 14x. Pause, go give it a try. Okay, let's look at this. This is going to be, we're going to need to use the chain rule in this because we have an inner function and we have an outer function. So we're going to need to use the chain rule on this one. So if we use the chain rule, we're going to find the derivative of the outer without changing the inner function. So the derivative of the outer, the natural log, is 1 over 14x multiplied by the derivative of the inner function, which is 14. Okay, we took the derivative of the outer. That's a natural log. Natural log is 1 over that inner function, so 1 over 14x. If we combine these together, I get 14 over 14x, which reduces to 1 over x. So is the derivative of every natural log going to be 1 over x? Because that seems awful coincidental. Let's try. I'm going to give you 2 more functions, and I want you to use some chain rule action on these. I want you to give those a try and tell me what you get. Or don't tell me, you can't talk to me, but go try it. So come back in 5 seconds. No, really, stop the video. Go try. Okay, welcome back. I hope you actually tried. I'm going to move this first one up so I have a little more space. Okay, if we use the chain rule on this first one, m prime of x, derivative of the natural log, so the outer function would be 1 over the inner function unchanged, multiplied by the derivative of the inner function, which is 4x plus 3. If I simplify this by multiplying those two together, I get 4x plus 3 over 2x squared plus 3x. So no, it's not always going to be 1 over x. It kind of just depends on what the inner function is. Maybe you knew that already, but if you didn't, now you know. Okay, I hope you tried the second one as well. So for n prime of x, the derivative of the outer function, so that would be 1 over the sine of x, multiplied by the derivative of the inner function. The derivative of sine is cosine. And then if we combine those together, I get cosine x over sine x, which is an identity you should know. Cosine x over sine x is cotangent x. That's not something you have to memorize, but it's something that's good to know, that the natural derivative of a natural log of sine x is just cotangent, interestingly enough. Okay, I'll see you in the next video. The next one will be short.